Hey guys, so I hope that your week home is going all right and that everybody's feeling good. This first video is really just review because a lot of you were absent for the first like 1 or 2 days of the unit. So you really only need to watch this video if you have some things missing in the beginning of your note packet, or if you just feel like we did acids and bases a really long time ago and you want a little bit of a review before you do the practice questions on CASA Learning. All right, so let's just start with like how to tell if something's an acid or a base. My first suggestion would be to look on your reference tables. So if we scroll down to, where am I? I went too far. Okay, so here's tables K and table L, right? And table K has a bunch of acids on it, and table L has a bunch of bases on it. So just from looking at these tables, we can see that all of your acids, or most of them anyway, they start with the letter H, right? So if something's not on this table, but you want to know if it's an acid, you want it to start with the letter H. For bases, again, if you notice what most of them have in common except for the last one, they end in OH. They end in the hydroxide ion, and they start with Na, K, Ca. What types of elements are those? They're metals. So bases, if they're not on this table, but you want to know if something is a base, it needs to start with a metal. It needs to be ionic, and it needs to end in OH. Okay, so when we write down the definitions for acids and bases, they're a little more confusing, but that's really all they mean. So let's go back to our notes. I'm going to get a pen here. Okay, so Arrhenius is this guy, and he defined bases that way and acids. If it starts with H, another way of saying that is that it releases hydrogen or hydronium. So that just means that when you take something like HCl, which is an acid, and you drop it in water, even though it's not ionic, it's going to break up into pieces like an ionic compound would, and one of the ions is going to be the hydrogen ion. And that hydrogen ion, when that is present, that's what makes the substance an acid. Now, hydronium, if you look on table E, and I'm just showing you guys this because a lot of it you don't have to memorize, so you don't want to make your life harder. But if you find hydronium on this table, it's actually the first ion right at the top there. So water's H2O, right? When hydrogen ions are in water, instead of like floating around by themselves, sometimes they add themselves onto water. So what does H2O turn into if you add an extra H to it? H3O. So that's why we say for acids, we can either make hydrogen or we can make hydronium, which is just when this H that was by itself adds itself to water, but they both mean the same thing. Bases are ionic and end in OH, but how you'll see that worded is that it'll release hydroxide ions in solution, which again, guys, is a fancy way of saying when you put a base in water and it dissolves, it's going to break apart into ions. So let's take NaOH as a base, right? This is going to split up into Na, but the OH ion floating around is what is going to make the solution basic. So anything that makes these ions in solution is going to be classified as a base. Okay, so now if you go back to table L, there's a base on that table that does not belong. Can you guys find it? Which base on this table doesn't fit with that definition? NH3, right? So Arrhenius got credit for that definition of an acid and a base, but these other two guys came along, Bronsted-Lowry, and they said, well, NH3 does all the things a base is supposed to do, so we need to come up with a new definition to fit NH3 in. So the way you can remember this is this theory is bad. So that stands for bases accept and acids donate. And when we're talking about accepting and donating, we're talking about hydrogen ions, or they can also be called protons. So in the Bronsted-Lowry theory, OH doesn't matter. It's not like in the Arrhenius theory where it makes something a base. Okay, so here's what we do to figure out in a reaction like this, which one's the acid and which one's the base. I'm going to take the substances on opposite sides of the arrow that have the same elements in them. So these both have N and H in them, right? And I'm going to connect them. You want to think of what can accept and what can donate. Usually if you're willing to donate something, it means you have extra of it, right? Like when you donate your clothes or if you donate food, you're donating because you have extra. So it's the same thing here. You want to think about which of these things has extra H's, NH3 or NH4. NH4 has an extra H, so it's going to be able to donate. And according to this theory, what kinds of things donate? Bases accept, acids donate. So this guy is going to be my acid. It's going to be able to donate. And the thing on the other side is going to be the base. If it has less hydrogens, it's going to have to accept. Right? Then I want to connect this and this. Again, they both have the same elements in them. They both have H and O. Which one of these has extra H's? H2O, that has more H's, right? So if it has more H's, what is it going to be able to do? Donate, making it an acid. And making the other thing it's attached to a base. So depending on which scientist they're asking about, there's different ways of telling if something is an acid or a base. Properties just means in general what these substances are like. So if it's an acid, it's going to turn litmus red. It's going to taste sour, even though they'll tell you never to taste it. You have to know what it would taste like. Acids are electrolytes. That means that they conduct electricity when they're dissolved in water. And they're corrosive. So that just means like if you take a metal and you dump acid on it, the acid is going to corrode the metal. The metal is going to look like it's dissolving, but it's really like reacting. Bases, they turn litmus blue. Okay, they taste bitter. So a lot of people think that sour and bitter are the same. Sour would be like if you bit into a lemon. Bitter would be like eating dark chocolate. So they're a little different. Bases are also electrolytes. They also conduct electricity when you dissolve them in water, so that's not a good way of telling them apart. And for reactions, we call them caustic, which means like acids, they're going to hurt you right away. If you spill acid on your skin, it's immediately going to look a little irritated. It's going to immediately feel like it burns a little bit. Where bases being caustic means you can spill a base on your hand, and at first it's going to kind of feel cold. It's going to feel like a little slippery, and not until later is your hand going to look irritated. So its reaction is not as quick, or as like, you don't notice it as quickly, I guess. All right, so finally, this word electrolyte is kind of like a new word. When you guys think about the word electrolytes, what drink do you automatically think of? Gatorade, right? And if you think about what kind of people drink Gatorade, athletes. And if you look at the stomach of this athlete guy, what do you notice he has? He has abs. So from now on, you're going to start seeing questions. Which of the following is an electrolyte? If it's an acid, that could be an answer. If it's a base, that could be an answer. The S in electrolyte or in abs stands for salt, which is another word for just a regular ionic compound. So all three of those things could be acceptable answers. Okay, so here's those tables, guys. Again, before you do any thinking, always check here. If it's on one of these tables, it's an acid or a base, and you don't even have to think about it. Okay, the next part of this unit talks about pH. So the pH scale is also a way of telling if something is an acid or a base. It goes from 0 to 14, 0 being the most acidic and 14 being the most basic. And then 7 right there in the middle, if you take a look at your little chart here, it has an equal amount of hydrogen and hydroxide ions. So it's almost like acid and base canceling each other out. If you have a pH of 7, that means you're neutral. Okay? So over on the acid side, what type of ion do you notice you have more of? You have more hydrogen ions. So anytime you have a pH below 7, you know there's more hydrogen ions in your solution. For a base, we're going this way on the pH scale. So what kind of ion is there more of? There's more hydroxide ions. Okay? And then if we're neutral, like water, for example, water is going to have hydrogen and hydroxide ions in it, but the amount is going to be equal. So the pH is going to be 7. It's going to be a neutral solution. Okay? All right. What kinds of questions can they ask you regarding to pH, or what relationships do you have to know? Another word for the amount of ions in solution is concentration. And the unit for concentration that we've talked about already, oh, I'm writing all over my paper, hold on, is molarity. So this capital M stands for molarity. It's a number that represents how much hydrogen is floating around in my water, right? So if you notice the relationship, whatever the pH is, the exponent of the hydrogen ion concentration is equal to that, but as a negative number. So you're never going to have to calculate this, but you would have to notice a pattern and be able to fill in the blank. So if that's my pattern, what would be the hydrogen ion concentration if the pH is 2? Well, we just said the exponent in negative version is equal to the pH. So 1 times 10 to the negative 2 would be the molarity there. So guys, as my exponents are negative. As my pH goes up, what's happening to hydrogen ion concentration? It's going down, right? Because if my pH is going up, I'm moving away from the acid side. So my amount of hydrogen ions is going to be less. Okay, and that's all you really have to understand about that. Another thing that's kind of weird is that for every 1 jump you make on the pH scale, that's a 10 times change in hydrogen ion concentration. Look what we did up there. We changed the exponent by 1. That's the same as moving the decimal over 1 spot. That's the same as multiplying or dividing by 10. So if I have a pH of 0, that's 10 times more acidic than something with a pH of 1. If I have a pH of 0, that's 100 times more acidic than something that has a pH of 2. 2 jumps is 10 times 10. So however many 0 there are, that's how many jumps you need to make on the pH scale. So let's look at example 2. An acid with a pH of 5 is 100 times weaker. So 100 times means I need to jump 2 spots. I either need to go down to 3 or I need to go up to 7. So if 5 is weaker, then you want to look for the stronger acid. Which one's a stronger acid, a pH of 3 or a pH of 7? Yeah, pH of 3. If you said 7, you're lucky I didn't hear you. All right, same thing here, guys. So now they're saying I'm 1,000 times more. So that's 10 times 10 times 10. That's 3 jumps, right? Here I'm lucky because if I'm starting at a pH of 1, I can't jump down 3. My pH scale ends at 0. But let's actually go through this question. They're saying if I have a pH of 1, I have more hydrogen than the other acid. So if you have more hydrogen, you have a lower pH. So if the other acid has less hydrogen, it's going to have a higher pH. How many times higher? 3 jumps. So I'm going to jump from 1 to 4. Does that make sense? I hope. All right, guys. So if you missed any of the unit, this was it. The first Kessel Learning assignment that you guys were assigned has to do with all of this, identifying acids and bases and looking at the pH scale. So I'll see you at Extra Help if you need to come, and I'll talk to you guys soon.